cry. Welcome back to this channel. In this video, I'm going to be teaching you growth models. All right. Eventually, we are going to be ending at the Von Bertalanffy growth model, but we will not start with Von Bertalanffy. I'm going to start with the simplest of the models, and then we are going to go to the more complex ones, okay, until we'll build it up to Von Bertalanffy growth model. I want you to see how over time those models were built upon their limitations and the reasons why they had to be another model, okay? And I'll tell you the field of study in which Von Bertalanffy is one of the best that is being used. So I'm going to be speaking practically in the context of fisheries in this video, okay? So I'm going to be modeling this thing in the context of fisheries. And there are four models that we're going to be considering. They are the linear model, we're going to see the exponential, then we'll see the logistic model, and then the last one is the Von Bertalanffy growth model. Now, like I said, I'm going to show you how they started off and then saw their limitations, then advanced to the next one and advanced to the next one. Yes, this is also their chronological order of development. So first, why do we model? Now, the reason why we model is we see a particular biological condition, a particular biological phenomenon, and we try to explain it mathematically. We want to use mathematics to explain what is happening in a population, in a given environment. We want to use mathematics to describe it. So we do what is called modeling. Okay? So in time past, the simplest form of modeling that existed was the linear model. And what the linear model say? It basically idealizes a linear relationship between two or more variables, okay? And in this case, we're going to be dealing with two variables, basically. So we said in the linear model, from the word linear, you can already tell line, right? In the linear model, we are going to be idealizing the condition of our population increasing over time by a particular constant factor, and that constant factor is called the gradient. Remember, since it's a straight line, is a linear model, it's going to give us a straight line equation, right? And what is the one thing that is fundamental to straight line equations? They have a constant slope, right? What is slope? M equal to what? Change in y. For the gradient intercept, we're going to have change in y, that is delta y over delta x. In this case, if we have intercept, it's going to be y minus y intercept over x. By the time you cross multiply, you will have y and you make y subject. You will have y equal to mx plus c. So this is the root of the equation that we're going to be talking about, where we have just two variables, y and variable x. In this case, linear model is used to like I said, generally, we could use modeling to talk about a population, okay? But in this case, we want to look at two things, two parameters that are pertaining with fish. And those are the length of the fish and the weight of fish, or the length of different individual fish or the weight of individual fish, or the entire biomass. Exactly now. So in this case, using length, for example, we want to model linearly by saying that the change in length per unit time, the change in length, that's dl dt, which is what we did here. The change in y-axis to the change in x value is constant m, right? So here also, the change in length per unit time is going to be a constant. In this place, we use k. I repeat myself. You know here, slope is constant for a straight line equation. If I had something like y equal to 2x minus 3, the slope of this thing is what? 2. It's a constant value. So, and the same way here, we are saying that the change in length of fish, in length of that organism, or fish in this case, per unit of time is going to be constant, meaning that it will grow at the same rate over time. So for example, if every 2 years your fish increases by 5 centimeters, in 6 years, how many centimeters will your fish be? It will go by 5, 5, 5, 5. That will be 30 centimeters longer, isn't it? If fish is growing 5 centimeters per year, right? In 6 years, it's going to grow 30 centimeters longer than it was. Is it clear now? So that is what that thing is basically saying. This equation is saying that every time per time it is growing at the same rate. All right. So by the time we bring in do separation of variables, we are going to have dl equal to k dt. So from here, I basically cross multiplied. Then from here we integrate. Look at me talking to you like you understand what I'm saying. You integrate. The integral of dl will give us what? L. The integral of this is going to give us what? The integral of this will give us our constant kt, then plus c. Okay, if you integrate a constant, you are going to get a linear term. All right, so and that's it here. Is plus c. All right, so it means that this is the equation, and this equation means that the length at a given time is going to be the constant of growth, constant rate of growth times the time plus c. Now, what's c? C is the initial condition. How are you? Good afternoon. Good evening. How do we know the initial condition in this case? The initial condition is the length that the fish, length of the fish at time 0. When time is equal to 0. When time is equal to 0 here, if you plug in your value, what are you going to have? You're going to have L at 0 equal to 0 times K plus C. From here, this becomes 0. It means that the length L0 will go what? C. So, it therefore tells us that this L0 is C. It means that we can modify our equation, therefore, to become L at a particular time to be equal to what? KT plus L0, where L0 is equal to what? Initial length of the fish. Now, why does this model not fit in for fish, for example? The reason is because it has some fundamental assumptions. The first assumption is that the length of fish increases regardless of the condition at the same rate over time. And it will continue to increase with time, okay? Which is not true. So it is biologically unrealistic. So because of that, the model is abolished. The linear model is abolished, and that's the limitation. It is biologically unrealistic. Why? Because as the fish grow or as the organism grow, the rates at which it is going to increase in length will not be as much as it was growing when it was younger. Yes, even as humans, for example, we tend to grow faster when we are younger than when we attain a particular height, for example, we stop growing. Okay, we stop growing. Our growth stops, and that is actually because we are humans, though. Because in that context, I would like to also let you know that there are two types of growth. We have the determinate growth, and the indeterminate growth. So we humans undergo determinate growth, but organisms like fish undergo indeterminate growth. Why is it indeterminate? Because they have what is called growth spurts. They experience, rather, what is called growth spurts. Growth spurts. And what is growth spurts? Growth spurts are basically growth spurt simply means period of growth and stopping to grow. Grow, stop to grow, grow, stop to grow, and etc. Now, because of that limitation with linear model that I mentioned, the fact that it is unrealistic, and the fact that fish does not grow at a constant rate, it grows faster at a younger age than, and then of course, environmental factors also limit growth and all of that. The environmental factors are not constant. That's one of the things, okay? So because of that, then there is need for a better model. And the better model in this case is going to be the exponential model. The exponential model. The exponential model. Now, what does the exponential model idealize? The exponential model was first developed. Um, it wasn't exactly developed alone by him, okay, but his idea for the integration of exponential model into the population, that idea came in 1798 by Thomas Malthus, Robert Thomas Malthus. So he was one that, you know, Malthus, I think. He was the one that formulated the Malthusian population model. And what was the model about? He said that population increased at an exponential rate while food increased at an arithmetic progression. Okay, so it was from his ideology that it was integrated into studying, you know, parameters like length and weight for fish. Okay, so and they, you know, thought it could work with the weight of fish, for example. We don't use this guy particularly for the exponential model for the length. We practically use it for weight, and you will see the reason by the time you at the end of this lesson. So like I said, what does the exponential model tell us? It tells us that, you repeat it, and no, like the inside, yeah, okay. Okay. Has it gotten spoiled before? No, it's not this thing that okay, okay. Okay. So initially we said that what was I saying? Now the exponential model, So in the exponential model, what we are saying is that what the exponential model says is that the rate of change in weight of an organism per unit of time is directly proportional to the weight at the particular time. Let me put that in context. I said exponential model presupposes that a fish will change its weight according to the rate at which it will change its weight will be directly proportional to the weight at a particular time of the fish. So meaning that if the fish has a small weight at an instance, the rate of change in that weight will be also small or will be slow. But if the fish have a larger weight, the rate of change of weight will be faster or larger. Okay, now let me now rephrase. What that is saying is that small fish grow slower, while larger fish grow faster. Do you now understand? So that's exactly what that thing is saying. And what does it idealize? Remember that growth is anabolism minus catabolism, right? So it is saying that as the fish grows, it's going to experience faster anabolism, okay, than when it was younger. And that's the truth. It experiences faster anabolism, okay? So, mathematically speaking, the model says therefore that the rate dw dt, the rate of change in weight dt, will be directly proportional to the weight at a particular instance. So what this means is dw dt will be equal to, we introduce our constant of proportionality. In this case, it's going to be called rw. Now, R here has a special name. It's called remember that our K in linear model is the growth constant. This one, R here, is called the intrinsic growth rate. R is called the intrinsic growth rate. Now, what is the intrinsic growth rate? It is called intrinsic because it is peculiar to a population. So there are populations that will increase in weight faster than others. For example, the rate of growth of a fish like dolphin or shark will be different from the intrinsic growth rate of a tilapia. Do you understand what I'm trying to say now? It will be different from that of a catfish. So it is peculiar to a population. This R, exactly. It is not just constant for every population. It is reserved for every population. That's why it's called the intrinsic rate of growth. So by the time we make this into complete maths, we are going to, do the same thing, separate variables, and then we'll have the W dt, the W will be equal to, the W will be equal to RW dt. Now, when we separate variables, we are going to divide both sides by W, so that this becomes 1 over W dW is equal to, W takes care of this, is equal to R dt. So from here, we are going to integrate this. I integrate both sides actually. By the time I integrate this, I'm going to, if you integrate 1 over W dW, you are going to get ln W is equal to, if you integrate a constant again, what will it give you? To give you a constant times the, what's it called now? The variable of that you're using to integrate. So in this case is t, so it's going to be rt, then plus the constant of your constant of integration. So now, what does ln w mean? So ln w is equal to rt plus c. So ln w means log to base exponential of w is equal to rt plus c. From here, exponential goes here, and then we have w equal to exponential rt plus c. Exponential kicks all this thing up. If you remember logarithm, remember in logarithm that if I have log to base a of x is equal to m, for example, x will be equal to a raised to the power m. This base will kick this guy up. So the same way is what we're going to do here. This guy will come and kick everything here up, and w becomes e to the rt plus c. So, but of course, recall also, please recall again that a raised to the power m plus n is the same as a raised to the power m times a raised to the power n, right? This is where it came from. Remember, multiplication of base leads to addition of power, right? So we can therefore say that w will become e raised to the power rt multiplied by e raised to the power c. So from here, this is constant, and this constant is going to be our initial condition again. Is it clear? So e raised to the power c becomes w sub naught. That's the initial condition. And I'll prove it to you maybe after I've derived it. I might use a question to prove it to you. Therefore, w becomes w sub naught e raised to the power rt. Okay? So, and this pretty much becomes the equation. So w sub t, that is weight at a particular time, is going to be the original weight, or the weight, the initial weight. W sub naught is going to be the initial weight of the fish, or the initial biomass, and the w sub t is going to be the weight at the time, at a particular time, at a specific time that you are calculating, okay, at a given time. Then E, of course, is Euler's number, right? 2.71828 or something. Then R is going to be what? The intrinsic growth rate. So I just put IGR, intrinsic growth rate. I already mentioned that here. Then T is the time at which you are calculating, the given time that you are calculating. Just to prove that W sub naught is the initial weight of the distance. Keeping in mind that this is our original equation now. This is our equation. What will be the weight, therefore, at t equals 0? So when t equals 0, when t is equal to 0, you are going to plug that into the equation, and then you have W sub t equal to W sub naught, W at times 0 then equal to W sub naught e raised to power, what is R here? R is any given R times t, which is now 0. R times 0 is 0, e raised to power 0, 1. So the weight at that time will be what? W sub naught. So that tells you the weight at time 0 is W sub naught. So that's why this guy is the initial condition. Now, graphically speaking, how does this look? The graph of this, which is going to be weight against time, is going to look something like this. Now, I'm going to explain the graph because the graph is of specific importance to our modeling as well. See, I mean, of course, it's not going to start from the scratch here, so let's say it starts from somewhere here. But notice something, that it has a vertical asymptote. Now, what does a vertical asymptote mean here? This vertical asymptote tells us that our weight can go to infinity. That's what it's saying, that the weight can go to infinity at a given time. The weight will continue to increase and increase and increase, and you definitely know that fish don't grow that way. Exactly, the weight of fish cannot increase that way. I mean, like I said, they have growth spurts, okay, which means that they will grow for a while. When the condition is unfavorable, they will stop to grow. If you multiply the conditions that could make them grow, they are going to grow more, are going to grow faster. Do you understand? So it means that they necessarily don't permanently stop growing, only that the rate of their growth may slow down at a given time. Do you understand? So that is one of the limitations of this guy. It idealizes that the weight of the fish will increase forever, which is not true. Okay, in fact, if anything, it may diminish under very under adverse conditions, and may increase again under very suitable conditions. So this graph is, but one of the logical thing about this graph is that it tells us that the weight is going to start from somewhere, which is the initial condition in this case, and it's going to increase in weight slowly, which is true. The fish will first increase in weight slowly, but after a while, the rate of increase in weight is going to be what? Exponential, and that's true. It's going to be exponential. And this exponential growth happens between the fingerling stage of the fish and the juvenile stage of the fish. So that's why children grow faster when you give them food, good food. But adults don't necessarily grow again no matter the kind of food you give to them. They may increase in weight a little bit, but they don't necessarily grow as fast as the kids grow. So that's why somewhere around here looks like exponential. Okay, because if you compare the time, look at the time from here to here, but look at the concomitant increase. The increase is very small. But compare here, this place to this place. Look at the time, almost the same as here. But look at the increase. Look at the increase. Very great increase. Do you understand now? So that is why the exponential growth works a bit, but of course is not still the best model for a fish population. Not fish population. Generally speaking, speaking of the weight, for the weight of fish, it is not a good model. Now, in the next model, which is called the logistic model, I'm going to be showing you a better model that explains, that is more biologically fitting, okay, even though it's not still the best, okay, but it is more biologically speaking fitting for a population of fish. And in fact, that is why it is called the logistic growth model. Now, why is it called logistic? It is called logistic because it is logical. It fits in all the biological parameters that may affect the fish. Okay, it's still showing, right? It fits in all the biological parameters, or at least most biological parameters that the exponential model does not factor in. Okay, now it was invented by Verlust, Pierre, Francois, Verlust, in the year 1838, yes. The way to remember is this one is 1798, this one 1838, then the Von Bertalanffy 1938, you see? All right, so, and his model was very nice, okay? And that's why it probably persisted for as long as 100 years like that, 1938, before this guy now revised it, this guy, Von Bertalanffy. Now, What did this logistic model say? The logistic model factors in two things. First, that the rate of growth, like we have said here that rate of growth in an exponential model is actually born on exponential model, but it factors in other parameters such as the environmental conditions that might affect the growth of the fish. Okay, so that's why the graph of the logistic model looks like this. So we're going to start from the graph here. It looks like this. So it's a sigmoid curve, a sigmoid curve. Now, what does this sigmoid curve mean here? S-shaped curve. What does it tell us here? It tells us that rate of growth, what's it called now? Rate of growth is slow at the beginning, which is true. But somewhere here, it becomes very rapid, okay? So, but here's the thing. You see, conditions like, there are two major factors that affect the growth of fish. The first one, we call the first one intrinsic and the extrinsic factor. Intrinsic. Now, what are the intrinsic factors? Those are the factors that are uncontrollable by the breeder, okay? And what are the intrinsic factors? Intrinsic, they include the genetics of the fish. Okay, there is no how you can breed tilapia that will ever be as big as a shark. Do you understand? So that is genetically speaking, the fish is already limited in its growth. Another genetic factor is the age of the fish. Age of fish. Okay, because at senescence, the fish can no longer grow as fast as it used to be. At senescence, catabolism will be greater than anabolism. Catabolism will be greater than anabolism. So because of that, the rate of fish growth is going to be limited. Okay, and that's why we have this phase here. We call it the stationary. No, the first phase is called the lag phase. It's called the lag phase. Then this phase here, being exponential, we call it the log phase. The log phase. Okay. Then here is the deceleration phase. The phase where the rate slows down, okay? Then this phase here is called the plateauing. It actually tapers off, okay? It's an asymptote as well. It's an asymptote, but this time a horizontal asymptote, okay? So, and it's called the plateau state. The plateau phase, rather. Plateau phase. Now, what does this tell us? Now, I'm going to show you why its limitation as well. So, it grows and it begins to reduce at senescence. For example, the fish, the rate of growth begins to reduce at senescence. All right, but the plateau phase is where it tells us that the fish stops growing at the time. It just stops growing totally. So now this growth is best for humans because there's a time when you can no longer increase in height again. Okay, for example, in height, but you can still increase in weight. Okay, so you can already see that plateauing here does not still work for organisms like fish, maybe even for humans, because if you feed people, even at 30, 40, they will still grow fat. Yes, and they will still increase in weight. So meaning that this plateauing for weight is not exactly the case. It's not perfect, okay? But it is logical. It's a logical model because it tells us that other factors tend to limit the rate of its growth. All right. Some extrinsic factor, however, extrinsic factor include the following. Extrinsic factors include the one that the breeder can control. They include things like feed. You understand? Feeding, availability of food. Okay. Disease control. That's environmental factor. Presence of predator now. Some are biological, others are chemical. Freshness of water, okay. The availability of DO2, that's dissolved oxygen, and stocking density, a very vital one. Stocking density. I hope you know that these also predisposes the fish to disease, or maybe even invasion of predators, or maybe even internal predators, because some fish, because of high stocking density, if they are shooters, that is one that goes faster than the others, they might tend to become a predator in the system. So that's just it. Now let's mathematically model this logistic model. And you're going to see that it is very logical. Maybe I should clean this place, guys. Now, what does the logistic model say? The logistic model says that the rate of increase in weight, that's the WDT, is directly proportional to not just the weight, but also directly proportional to the amount of space. So in this place, it's also the space or the environmental conditions, factors that affect growth. So in this context, we are going to streamline it to just the space, available space for increase in weight. Do you understand now? So it's direct proportional to the available space. Now, available space here is going to be given this way: 1 minus W over K. Then you ask me, where did I get this from? I'm going to show you. You see, the space available will be a ratio of the amounts of space that that environment can take. So what that means is that if in that environment the amount of fish or the weight of fish that is sustainable over a period is 100, if the weight of the fish at that time, at a particular time, is 20, it means that it still has space for 80 grams or 80 kg, whatever the unit is, of expansion. It still has 80. Do you understand now? So since it's not a fraction, we now subtract it from here, which is going to be 0.8 in this case, 0.8. I hope you understand what I'm trying to say. That is, if the carrying capacity, okay, K is carrying capacity, I'm going to define my parameters. If the carrying capacity is 100 kg of fish, and only 20 kg is all we have in that particular time, it means that the space available for growth is still a further 80 kg. Do you understand now? So how did I get the 80 kg? I basically subtracted the 20 from 100. All right. So if I take it as a ratio, the ratio of the present weight, extant weight, such as we have here 20, over the carrying capacity, which is 100 normally. So when you subtract it from 1, you're going to have the space that is available for growth. Do you understand now? So together, I could therefore say that the W dt will be equal to W will be directly proportional to W into bracket 1 minus W over K. So from here, therefore, we know that the W dt will be equal to our constant R, W into bracket 1 minus W over K. So in like manner, we are going to do first order differential equation, which is separation of variable, using separation of variable, right? So first, I like to make this one look nice so that it becomes the W dt equal to RW into bracket K minus W over K. By the time you make the fraction a single fraction, LCM is K, 1 in K times 1, K minus K in this one. All right. So from here, therefore, I bring dt to that side. So I have, and I bring K to this side. So I have K dW will be equal to R omega into brackets K minus W dt. Divide both sides by K minus W over K minus W. This takes care of this. So I have from here K dW over K minus W is equal to RW dt. But of course, I said we are separating variables. So what am I going to do here? I'll divide both sides again by W. Okay, so if I divide both sides by W multiply this base here, 1 over W. So this takes care of this, and we have K dW over W, K minus W, close brackets, equal to R dt. I hope you understood what I did here. I multiplied both sides by 1 over W. So this side times 1 over W. W cancel out. And here, this place times 1 over W will give us this. Is it clear? So in order for it to look proper for integration, I'm going to have integral of k over w into bracket k minus w dw equal to r dt. So from here, I can solve by partial fraction. So I will solve by resolve the partial fraction. That's how we write it. Resolve by partial fraction, or the partial fraction on this side. Partial fraction. So I have k over w into bracket k minus w becomes 1, a particular constant, a over the first thing here, plus a particular constant, b over k minus w. If this becomes the case, is this I showing? Okay. So if that becomes the case, I could, from here, I'll multiply both sides by this denominator. Multiply through by w into bracket k minus w. So if I multiply this side by w into bracket k minus w, I have k will be left here, right? If I multiply this side by this, if I multiply this one alone by this thing, this one will cancel w, it remain k minus w. So it will be equal to a into bracket k minus w plus, if I multiply this thing by this thing, it's going to give me, this will cancel this, remain w, bw. From here, therefore, we have k equal to ak minus aw plus bw. Now, what does this tell us? Only these two can give us k, right? They are related. So k is equal to a k. Divide both sides by k. A becomes what? K cancel k. A equal to what? 1. Isn't it? So then from here, minus aw plus bw will be equal to what? There's no w here, so that's 0w. Make sense? So that b minus a all w is equal to 0w. W cancel w, and b minus a is equal to 0. B will be equal to what? A. So since a is 1, comma, b will be what? B will be 1. Is it clear? So if that's the case, our partial fraction has been resolved to k over w over k minus w equal to w into bracket k minus w equal to a is now 1 over w plus b is now 1 over k minus w. Alright, so we input this into our integrand again, so that it becomes integral of 1 over w plus integral of 1 over w dw. Should I bring it to that side? Yeah, it should contain here. Plus integral of 1 over k minus w dw. Okay? Alright, it will be equal to integral of r dt. Is it showing? Integral of r dt. Okay, let me move it a little. Alright, so if that's the case, therefore, integral of this will give me what? Ln w, right? Just like we did in the other place. Plus integral of 1 over this will give me ln this again, right? Ln absolute value of k minus w. Okay, no. Because our variable of integration w is here and is negative, it's going to be negative ln now. Is that okay? So plus minus this is minus this. So ln k minus w is equal to integral of this again gives us RT plus constant of integration. So from here, you know therefore that this becomes log to base exponential of W minus log to base exponential of K minus W is equal to RT plus C. So from here, we know that log is common, log to base exponential is common between W. Now, in logarithm, you recall that if we have log A minus log B is equal to log of A over B, right? So I'm going to take a fraction of this too, becomes W over K minus W. Exactly, okay, that was what we had. Okay, no, it's different. So this is equal to RT plus C. From here, therefore, E goes there and we have W over K minus W is equal to E to the RT plus C. So from here, what do we do now? What do we do now? What do we do? You know that from here, what do we do? If we multiply through, it becomes W equal to K minus W into bracket E to the RT plus C. All right? E to the RT plus C. But from here, we also know that W will be equal to, we know that W will be equal to K minus W, close bracket. E to the RT can be written as ERT dot E to the C, right? So that W becomes K minus W E to the RT dot a constant. Let's put A as the constant. So if A is our constant, then let me come here. So if A is our constant, then we know that our expression becomes, this can open the brackets, W becomes A K E to the RT minus W, no, minus A W E to the RT. Okay, does this help our situation at all in this place? I don't think so. Does it help us in any way? Okay. Since we are looking for an expression for W, right? We want to write an expression for W. So this guy will come here. So we have W plus, or no, let's not stay alone. So it becomes AKE to the RT equal to W plus AW exponential RT. So that we factor out W, AKE to the RT equal to W into bracket 1 plus AE to the RT. Okay? So from here, W therefore becomes AKE to the RT over 1 plus AE to the RT. So I'm going to multiply numerator and denominator by E to the RT, no, E to the negative RT, so that to cancel out. And this one by E to the negative RT. That is still 1, right? So that this cancels this. Okay. But here is opening a bracket. Okay. So W becomes AK over 1, no, over E to the minus RT plus AE this will also cancel out now. This will cancel this. So this, right? Am I right to have done rubbish? Because E to the positive this, E to the negative this, yes, 0. 1 rather, yes, 0 then 1, you know. So, all right. So from here, we could also multiply by 1 over A. Multiply here by A to the minus 1 here. Multiply by A to the minus 1. If we do so, this will take care of this, and then we'll have W will be equal to K over AE to the negative RT plus 1. Because this one will cancel out here too, right? And that's the final answer. So W sub T, rate at time, will be equal to K over AE to the negative RT plus 1. And this is the standard representation of the logistic model. Now, one thing you will take note of is, let me define the terms. K here is not constant. It is the carrying capacity of the environment, carrying capacity of the environment. A here is the initial condition. No. Yes, A is the initial condition. Yes. A is the initial condition, because what did I translate to A here? What I translated to A was this guy here. So we can put it as S W sub naught. Okay, so if I write this equation, it becomes A will be W sub naught. If that becomes, so it becomes, our equation becomes K over W sub naught e to the minus RT plus 1. Then R intrinsic growth rate time, the time you are giving, then plus 1. All right, so because of the changing, because it's getting late, I'm going to show you Von Bertalanffy is the next one, okay? And so because of it's getting dark, so I cannot show you again. I'll show you tomorrow the Von Bertalanffy. So see it in part 2. See it in part 2 of this video. It's already getting dark. See you tomorrow. God bless you.